Hello everyone, welcome again. So I wanted to talk about what we're going to be covering during this workshop and briefly touch on the various topics and mention a few problems that we're going to be running into and how we're going to solve them and whether we have something in Houdini or not. Okay, so let me see. So we're going to talk about that in a bit. So the first thing, we have destruction. And with destruction, the main issue is how we're going to render that geometry. It's not so much about the sim or getting it done. It's more about rendering and making sure that it has enough resolution. Now, one way to add edge displacement, to add resolution, is to use edge displacement, and that will allow us to increase the resolution of the geometry at render time. One other thing that we should do is to transform the geometry at render time. Because we use PTC or points to deform the static geometry. So we take geometry, we fracture it, and then we transform it with points. The idea here is to export the static geometry one time. Okay, we cache it as whatever format we want, and then at render time we tell Mantra or Arnold to take that geometry, the static geometry at render time, and apply the transformation and apply the points. Mantra can do this, but the problem is if we have edge displacement and we're transforming a static geometry, it's going to be hard to multiply the vectors and apply the correct transformation to all the vectors that we need to displace the geometry. Okay, so that, for me, we're using Arnold, it's not possible. Even though I was able to get it to do the post-render transformation, I still could not get it to transform the points, the vector information, because the normal, if you have it pointing in the z-axis and then the piece is transformed somewhere else, you have to reorient that. So this plan here is off. We can't use this. So we have to rely on actual geometry. We have to rely on actual geometry, and I tried to keep it as low as possible in the scene and rely on edge displacement. Now this is something that can be heavy and will be heavy. It requires subdividing the geometry at render time and then doing all this calculation. And it depends on what you're capable of in terms of rendering hardware. You should consider using this or not. And then we have another thing, because this is a large scale shot with the ground collapse. We have a massive ground collapsing, and then we wanted the spaceship, when it rises, it still interacts with the geometry. So my idea for this, I'm gonna spoil it, is when I have two resolutions. Okay, so I have this one, which is when the ground collapses. You can see the cracks here. And I have another resolution of destruction or fracturing that only happens when the spaceship touches the geometry. And I separated it. If we look at the scene here, you can see I have separated the low res part, which is this, versus the part that the spaceship is going to touch. And that's what the spaceship is going to touch. I've made a system that we just do the destruction, the ground collapse first. We're happy with that. Perfect. We can work with the client to make sure that they approve that. We lock it in. We don't have to worry about that stuff anymore. Then we work on the second part, because if we keep changing both bits and make them dynamic, we're never going to get approval, because you change something, it's going to affect the other thing. So we have to lock it. That's my approach. I locked this bit, the ground collapse, done. A second sim that I did is using a subsolver to have the spaceship just go through that geometry and capture anything that touches. I isolated that geometry, which is this group. You can see random pieces here and there, but they're actually going to be affected in one way or another. And then I subdivided those again and run a secondary sim that has constraints in it. We'll go into more details. This allows me to focus on having only the details I need at the outer layer where I don't need extra details, and then keep the details only where I need them. Okay, so this is a very efficient workflow. And then if the director or the client comes and say, okay, I want more details, I want the debris to look like this, I want the pieces to be doing this, I can only work on that part. I only cache that part where the spaceship actually starts touching them, because all this part here, I have a version of this high-res geometry that matches this. It's a low-res version, and that's what I use up until the point before it the spaceship hits. When the spaceship hits, I start simulating. So this portion here is going to only happen after frame 145. So that's when this sim is going to be. So I don't have to be paying twice or more to get the sim working. And it's actually activating piece in a smart way, and we'll talk more about that. So it's only simming what is needed. If a piece is not needed it's not going to be active, it will use the previous sim. And the first layer was actually quite fast. So we'll talk about that more when we get to destruction weeks. Okay, let's go back. So we have that's for destruction, and that's pretty much it. It's not very, very complicated. There's other stuff like emission and stuff, but we'll get there. Okay, so now for smoke. When I talk about this shot, I'm gonna start with the complex one. So when I talk about this shot, I'm gonna call this the ground collapse. I'm gonna call this the crack shot. So for this one, you can see you have multiple cracks. So we have, as you guys saw, we have one block and about 10 sims here, and there's 10 more here, so 20 sims. And we're going to copy that. So 20 sims here multiplied by 3, that's 60 sims, all overlapping on top of each other, and they have to be high res and hold up enough. If we wanted to do different resolution for each block, we can definitely do that, or generate a low res version and use it as based on the camera distance. We can do that as well. But what I need is a smoke sim, and I need it to run it multiple times. Okay, and if we're going to store a velocity vector for these fields, it's going to use a lot of disk space, and we'll go into more of that later. We can, however, group all this and do a super crazy high-res sim, but that will require a lot of memory and may not necessarily save us anything at render time or in disk space. It could be a lot slower. So I needed to separate them. So a system that can, we need a system that will allow us to focus on one part, one cluster, and then we say, okay, I want to run it through all of these guys. So that's smoke sim. That's a multiple sim. And also for this shot, so that's one problem that we solved. So we need a clustering system. For this one, there's also a lot of problems, because if we wanted to push the resolution to the point where we have enough details for close-up, mid, and so on, we're not going to be able to do all that in one container. So what I ended up doing is splitting this into 4 segments. I call them, I believe, A, or cluster 1, cluster 2, cluster 3, and 4. And it's sliced it like a pizza, but just in 4 segments. And then I can work on this and make sure it looks great, and then run the sim again on all the other clusters. This is for the fire. Okay. Now let me tell you a secret. Now you see the fire here and the smoke. They're 2 different sims. I don't have smoke emitting. I don't have the fire emitting smoke. I would have loved to do that, but it actually is very expensive to render all that homogeneous volumes together, or anisotropic volumes. So I wanted to separate the fire. The other reason for that, if I'm going to have a smoke coming off of the fire, the director will say, okay, I don't want that. I don't like that. I don't like this smoke coming off of this fire. I want to change it. What will happen is that your fire will change. So you have this, when I decouple things, it's mainly for iteration purposes. when we have fire, just fire, we can focus on that, get it approved, done. The smoke is going to come from a different source, and that we can work on separately. And so let me turn these off. And so this approach helps me a lot with the sim, and it can defer things quite a bit. And because of this, I'm able to work on things quickly. I can distribute the task across multiple artists. If I wanted to have someone else work on that smoke, get it approved, they can do that, and I can focus on the fire, for example. And that's the approach. I did the fire separately, the smoke separately. Where was I? And then the other thing, I wanted to do the sparks, and I was showing in the top shot the sparks are, and the idea is based on the velocity. The velocity field is very expensive. Okay, so let's do a quick math, or let's do a calculator. Let's say we have 10 sims, okay, 10 high-res sims multiplied by 2, that's 20 for each crack. And let's say the file size for fire and density is 100 megabytes, just to be safe. Okay, and then let's do 20 multiplied by 100 megabytes for density and temperature, and 200 for velocity, which is conservative. So 300 total per cluster. So that's 6 gigabytes per frame. Okay, for 10 clusters. So let's see, 60 gigabytes for one frame, and if we multiply that by 100, that's 600 gigabytes just for one sim for one iteration. If we wanted to keep 10 versions, that's 6 terabytes just for one element. And I don't have that much capacity. We can't afford all that. So I needed a different system that will allow me to create sparks that follows the smoke sim, but without the velocity field. Okay, and I have a system for that. We'll talk about that later. And this mainly will mean that I can reduce this from 6 to 2. Okay, so I can reduce the disk space. Now another very important thing is that disk space is crucial not just for when you write, it's when you read. If we have 20 sims, okay, we're duplicating them 3 times. That's 60 sims. Each one of them, let's say 200 megabytes. Okay, that's 1.2 how many? 1.2 terabytes, I can remember. 60 multiplied by 0.2. So 1.2 gigabytes of data per frame. To read that is going to take a lot of time, okay? Or 12 gigabyte of data. To read that every frame, it's going to take a lot of time, especially if you have 150 megabytes read. It's going to take about 20 seconds just to stream that in. So we have to be very aware of all these things. If we're going to do production, we have to be very aware of how much disk space we're going to need. So for me, doing velocity caching is no way. I'm not going to be able to do that. And the top shot is actually very expensive. This one is easier because it has fewer sims. And I went with a much lower resolution for that top shot to save on disk space and make it faster to render. Okay, so we need a way to do sparks and have this interesting visual as well with the tornadoes, small tornadoes, and be able to iterate on each one of them. Okay, cool. So I clustered it to more than 4, and I will talk more about the other sims later. But basically, the center sim is separate from everything else. So I separated 4 blocks, and then I separated this center to be in its own sim. The reason for that is, again, I wanted to decouple things, because if the director comes back and say, okay, I want to have more smoke there, I can just change that. I don't have to resim everything. But if you were to start this without considering all that stuff, you would want to emit the fire from the smoke and then the spaceship to affect all of that, and then you get one comment from the director to say, I want to change the spaceship smoke to be 2 times denser, or to have more smoke there, you would have to redo everything. That's 1 week of sim. Just if you don't have resources, can be more, but it's a lot of time. So that's why I decouple things, because I can make them different. I can quickly iterate on them, and I can, if I personally, that's for me as well, because I iterate over this stuff a lot. If I wanted to have something different there, I would just change that bit for the spaceship, and it would still be able to get the stuff I want. Okay, let's continue. So another thing that we should consider is I wanted to have a large atmosphere. Okay, what does that mean? Well, you see there's a fog here. There's a volumetric light. Everything it has volumetric. You see this has volumetric. This is volumetrics from the mountain. I wanted to sim that. I wanted to have an actual atmosphere that is moving. You can see the God rays here, they're not moving. And I wanted to be able to do that, and I will show how we can do that. But unfortunately, it was I ran out of time, but the idea is to be able to cache all this data and do a giant sim that is not very high res, but can convey the illusion that this is happening, like something is changing in the atmosphere, because that's what will happen in this scenario. You will get a lot of dust everywhere. You will get a lot of movement and disruption in these areas. Though I don't have it, should be able to accommodate that in case the client asks for it. Rendering smoke plus fire plus sparks is challenging, as well as the illumination of all of that. So when we look at this stuff, it's actually quite complex to render, because what will happen is we have this light. Okay, will this light affect the fire or no? The fire is very bright, so this light doesn't affect the fire. Will any other light have to affect the fire? Most likely not. We want to have the fire be self-illuminating. Okay, so now we have this source. Will the fire affect the spaceship? Will the fire affect the smoke around it? Will it affect the sparks, or are the sparks only emitting light by themselves? They don't affect. Will the sparks be affected by this light? This main light. Will the atmosphere that we have affect any of this stuff in any way? Will the lightning affect the spaceship itself? All these links are very expensive. Okay, we have to always consider which one is going to affect which one is important to which one is going to be the most expensive bit to render. And for example, you can see I have volumetrics here in the entire environment. This light, all lights, they have volumetrics, but I don't have volumetrics from the fire itself, because that's very expensive. Okay, so we need to understand the relationship between these various elements and how we're going to approach that. Now we have also the problem of the cracks, though the cracks, they don't last for too long, but are they eliminating the geometry or not? Are they eliminating the fire or not? Are they eliminating the atmosphere or not? We have to think about all these combinations, because that's what experience is. We have to know this stuff. We have to efficiently render the bits that will make the visual sell really well. Don't look fake, but they are very efficient. So all this stuff I prepare for. I plan in my head as to what I'm gonna do and how the links are going to happen between the various pieces. And you can see here there's also the actual dust and smoke. Will it be affected by the fire or not? Will I have multiple scattering caused by this source into this smoke? There's two separate things, Will I have that or no? Will I be able to sell the visual if I don't have that, or is it something needed? So all these things we have to either have experience on or test them, see, what's the rapport, what's the cost of rendering this versus that, and if it's worth it or not. So all these stuff I discussed, I think about. And always remember that we're going to be displacing all this stuff. all this geometry is going to be displaced. So a lot of memory usage. The rays are going to be traveling through a lot of details. There's so many things happening before it gets to the surface. And for example, the spaceship, will the spaceship be reflective or not? You know, will it reflect the smoke around it or not? And these questions are very expensive. They can make the render become very, very expensive. And so we have to think about all this interactivity things. Okay, so I talked about that. Okay, so then for the lava, how we're going to do this lava thing. You know, I have the crack shot. I have this crack with the lava flowing. How am I going to do that? Am I going to sim it? If I'm going to sim that, it's a huge, large environment. How am I going to be able to sim a huge, massive, you know, like a river, basically flowing of lava? Can I do something different? Can I use something procedural? If I'm going to do something procedural, how will I create the lava itself? You know, so all these things we have to develop. We have to do R&Ds for. I don't have solutions for them when I started, and but I ended up implementing, and I'm going to show my solutions. So we have to consider all these bits. Okay, so for the magical lightning, I called it magical. For the magical lightning, it's going to be particles and SOPs based. So particle sim and SOPs. We're going to have a growing geometry, the growing path. How we're going to do that, those growing paths. How we're going to find the end, the center and the end bit, where they're going to end, how they're going to travel, and how to get that nice tree-like structure. You know, it's only propagating correctly. And the interconnectivity, there is interconnectivity between the paths, and it's actually quite challenging to find to get this path. So you can see here it's starting to grow, and then this one, it's split. One went this way and one went this way, and this one went this way and this one went this way, and it kept going on. It kept continuing. So it's very clever as to how it's going to spread. It's not just one blast that's going to be bolting out. It's actually propagating and spreading as it goes through that geometry. And these cracks are matching the geometry. Now, will these cracks deform the geometry? If yes, how? Will these, will these magical emit any debris or cause any other things? If they will do that, how will it look like? Are they made of particles, curves, or something else, or volumes? Will they interact with the geometry lighting? How, if yes, how we're going to do that? So all these things I think about. And another major problem is if we wanted these cracks to deform, how are we emitting them? Are we creating them on a flat plane where the geometry is flat, or are they actually being emitted from here and traveling through? If yes, how will they deform with the geometry? Because our geometry is deforming at that point. You know, if we build this path like this, after 2 frames, it changed. It's here. So the entire system has to be deforming like everybody else. So how are we going to do that? How are we going to have it stick to the geometry? It looks simple, but it actually is really complex. And then here, you can see the end bits. When they reach, they emit this spark. And that times with the geometry getting flipped and interacting. So all these questions we have to answer. And then the interaction elimination, where and how. So basically, what element affects what and what's important? Will the atmospherics be affected by this, by that, and all that stuff we need to consider. Rendering passes, how I'm going to separate this. So I think about all these. Things as I progress. How I'm going to separate it in a very smart way that allows me to quickly iterate over things. Okay, I want to change the spaceship, I can change the spaceship. I want to change the color of the cracks, I can change the color of the cracks. I want to be able to control all of that. I want to turn off this light, I can do that in comp, all this. And I need to consider ways of that will allow me to do this, because when I do this render, I actually don't want to re-render it again. I want to do multiple small renders, iterations to test bits and pieces. But when I go full on, I test a couple of frames, start the comp. If they work great, I'm going to do this one time. But then you get feedbacks from the clients. You need to be able to address those. You can't go back and say, oh, I'm going to re-render this, I'm going to look at this. You have to be able to address that. So I need to provide myself or the compositor as much flexibility as we can to allow them to do that work. If they wanted to change this sparks to green, okay, or red, what if we integrated the illumination of this blue color into the main pass, into the main rocks? Then we wouldn't be able to change it. Doesn't matter what we do to the particle, it's always going to be blue. So we need to separate that so we can have that flexibility. So all this we're going to talk about, we're going to solve, we're going to create, we're going to do it. And last thing is I'm going to talk about the hardware and disk space. I talked about briefly. It's not a major issue, but I'll talk a bit more about that, and then we're going to talk about the compute power. Thank you so much for watching, and see you in the next video. Bye bye.